live session. This is the live session for week 10th, and we'll be starting today's session. Let me introduce myself. I'm Gagan Meena, and I'm a fourth year PhD student in Electrical Engineering Department at IIT Bombay. We'll start today's session. This is the week 10th live session for Economic Operations and Control of Power System NPTEL course. I hope you have been these live courses, live sessions have been helpful for you. Feel free to give your feedbacks for all the live sessions so that we can improve the way you want us to give so that you can benefit. The purpose of live session is that all of you can benefit. If you want the way these live sessions are being conducted to be changed, your suggestions are always welcome. We're always open to that. We can change the way. But for that, we need your feedback. So please kindly give your feedbacks. We will be following the same agenda which we have been following till now. We'll go through the overview of week 10 and then we will discuss some questions. I hope all of you remember the deadlines. Assignment 10th deadline is tomorrow, and 11th, 1 week after that, October 9th. And most of you are able to, those who have visited the portal, they can find the Google Drive link where you can find all the links for these live sessions, recordings of live session, as well as the PPT which I'm using for all the live sessions. Let us start with the overview of week 10. All week 10 was a continuation of week 9. So in week 9 we stopped or we started in this state estimation was introduced in week 9. And that was taken forward in week 10. So detailed discussion on state estimation, essentials, requirements, and new development, let's say. And here we discuss the modern, we'll say the modern state estimator. Which is a linear one, linear state estimator. Which uses PMUs. We discussed this last time also that when we have earlier, when the PMUs were not there, we had this SCADA, and with PMU came the WAMS, wide area monitoring system. The SCADA refresh rate was quite less. Here we get minimum 24 samples per cycle. One cycle is of 20 milliseconds, and we have 24. So it is around 0.8 sample each. One sample each every 0.8 milliseconds. So very fast, very fast refresh rate here, and we don't find that fast refresh rate. In SCADA, it's quite one sample in every second or so. So there's a lot of difference between the two. And that is also one of the challenge of integrating these two data to develop a hybrid state estimator. That also we'll see here, hybrid state estimator, and another was the dynamic state estimator. And the advent of PMU has also opened the doors or arena for this dynamic state estimation because of very fast refresh rate of PMUs. We can achieve a dynamic state estimate every millisecond. We can estimate the state of system because we have fast dynamic state estimator has to run every millisecond, and within 1 millisecond it should also be able to even solve the problem and why do the state estimation. So state estimator needs to be very fast. Even for a large system, it is able to do it. So that's amazing. We are going to see that all these things are very helpful for us, very important, we'll say. And these things have changed the way we have been operating till now. So now, because of PMUs, we have, yes, SCADA based state estimator was non-linear. And why was it non-linear? Because we had this, the measurements from SCADA were these active power, reactive power measurements, and the voltage magnitude. Angle was not available. When we use these in the power flow equations, which are non-linear equations, we need to develop the Jacobian, take inverse. Will not take inverse. We have already discussed. Inversion is a very costly affair, a costly operation computationally. Inversion is a very instead of that, we use decomposition techniques. We use this LU decomposition, or we can do QR factorization. Then we can do SVD, singular value decomposition. All these we can do because ultimately in the linear state estimator, all these are non-linear state estimator. Inversion we can do once we find the Jacobian, we can do these LU, QR, SVD. The Jacobian will linearize that. Jacobian is used to linearize. At every step, we are, for a small perturbation, we are trying to linearize that around a point using the Taylor series expansion. So that is Jacobian. So non-linear, we are linearizing using Jacobian, and then we are solving it. So this step takes time. And then here, this was for SCADA. Now PMU, we have current and voltage phasors. Both magnitude and angle is available. That makes the state estimator linear. We have a linear state estimator here, and that is why it becomes very fast. It becomes very fast. We can simply use the pseudo inverse here. You will also see in the least square estimation. This was the basic idea. What is the benefit of using the PMU? I will just erase everything. Yes. We discussed this. Yes. PMUs, we all know it's very important thing here now. Advent of PMU. Another thing that we want to see is this was a preliminary. We will not discuss it because you already know, you have studied all these things. Fourier series and transform already studied in BTech at UG level, and in mathematics we can just to develop this concept of discrete transform, discrete Fourier transform. This Fourier series was introduced just to give a quick recap of the mathematical concept. Then discrete Fourier transform was used for phasor estimation. From the discrete samples, discrete current and voltage samples. We get here voltage and we get here current and voltage phasor estimates. There are different ways. One DFT is one of them. Then we'll see one more, which is least square estimation. There are other also mimic filter. Then Kalman filter is also there. All these are different ways uh, to estimate phasor. And phasor estimation is an important part of PMU. It is discrete because it estimates or reconstruct the signal or the phasor from the discrete samples. Okay, then the main topic, another important topic was the optimal PMU placement. Although PMU is having very high refresh rate, and using that we can get a very quick and current snapshot of power system. However, it comes at a cost. PMU is costly. Therefore, we need to optimally place them in the network. Because installing PMU at each and every bus is a costly affair. And if we talk about India, then in India we have right now PMUs installed at all 400 kV and above substations. So this was the phase one. Now phase two, the government is planning to extend it to 230 kV and 132 kV and other substations as well. This was the phase one where PMUs were installed at all the substation 400 kV and above. Now they are planning to extend it to other substations, and that to develop everything indigenously. So here PMU was taken from not, I would say, foreign vendors, foreign companies. But analytics were developed at IIT Bombay, indigenously developed. Here, phase two, the government want to develop PMU also plus analytics both in India, part of Make in India program. Therefore, we will talk about this optimal PMU placement, which has been a problem till now. Because when we don't want to install PMUs at all the buses, we need to know what are the optimal buses which we can see, which can be equipped with PMUs, and still we can estimate the state for the entire system. And the last one is the hybrid state estimator. How can we combine the measurements from existing SCADA or conventional measurement or conventional measurement, and second one, PMU measurement. And do the state estimator using both the measurements. Now we will see here. This is the first topic, today's first topic, which is Phasor measurement unit. This is the basic idea of PMU. So what PMU will do, it will obtain its input to the PMU are these measurements, current and voltage signals from current transformer and potential transformers. So these are from the two instrument transformers. Then once these signals are obtained, so these are analog signals. These signals are converted into digital signals using A to D converter, analog to digital converter. That's why I call it. We are doing is sampling here. We are sampling the analog signal to convert it into digital. And then once we do that sampling, then we calculate the phasors using DFT. And then these phasors are time stamped using the GPS signal, global positioning system. These phases plus timestamp give us timestamped phase. phasors, then using the communication channel, they are transferred or transmitted to the control center. Okay. And this phasor angle information can be used to do so many things. So many analytics have been developed. We can do this system, we can know, and it can provide us information regarding the system stress. It can give information about the modes of oscillatory oscillations in the bar system. And then the important thing here is sampling. What should be the sampling rate? So for a signal, if in a signal there are several components, we want only the, here we are focusing only on the fundamental. The minimum sampling frequency has to be twice the fundamental component, the frequency of the fundamental component. We achieve this signal with the spectrum band limited to B hertz. B hertz here is 50 hertz. We achieve this using the filters, anti-aliasing filters, which will give us which will remove the higher frequency components. And then we will get the fundamental, and for that the minimum sampling frequency has to be twice the 50 hertz. So minimum sampling frequency for a 50 hertz signal has to be 100 hertz to recover the phasor. Okay, so this is used to avoid the overlapping of the spectrum, which is written here. You see, aliasing is a problem due to overlapping of sample signal. And for these, the anti-aliasing filters are used during pre-processing itself to eliminate the frequency signal beyond fs by 2. Here, if we see if fs is equals to 100 hertz, then it will remove all the signal beyond 50 hertz. Okay. And this should not be discrete Fourier transform here. We are still talking about the PMU here. Okay. We are still talking about PMU. These are the things which we get from PMU. We get the direct measurement of bus voltage and angle. We also get the direct measurement of frequency and the rock-off. This is called the rate of change of frequency rock-off, popularly called as rock-off. And then, yeah, we also discussed that it can help us in executing the dynamic processing algorithm, dynamic state estimation, because of a fast refresh, high refresh rate. Yeah, this is same, minimum 24 samples per cycle. That is one sample each 0.8 millisecond. We get a good, accurate, not, you can say current, most recent snapshot information of our system, and we also get information, relative information across all the buses. And because we get a current very quick snapshot, we can take quick corrective actions as well. Corrective or preventive. This is the entire diagram for PMU. Already you all of you know this. We have the measurements of instrument transformer. We have already seen it, part of it. This is more detailed CTPT. From here we get the voltage and current signal. We pass it through the filter. Then we do the analog to digital converter. Here we have analog signal. This becomes a digital signal, which is again passed through a digital filter. Finally, we get our digital signal here, filtered, and then we do the phasor estimation using DFT. And because this requires the frequency information, frequency is estimated using this signal, and this frequency also goes to the PLL. So this is done through this phase lock loop. The frequency estimation is actually done using the PLL. Yeah, so GPS receiver. PLL is an important part here. And because of this, we get the time-stamped signals. Time-stamped phases because of these two elements, GPS receiver as well as this PLL. This is one example for discrete Fourier transform, how to calculate DFT. Here we see we have 8 samples per cycle. So N here is 8. Fundamental frequency 50 Hertz. If N is 8, what would be the sampling frequency? Sampling frequency would be N times F, which will be 400 Hertz. To calculate the sampling frequency and sampling time. So what will be sampling time here? (20 millisecond) divided by 8. How much is this? 2.5 millisecond. And frequency becomes 400 Hertz. The first part is very easy. Here calculating sampling frequency and sampling time. Now second part is to estimate the phasor. For this we have to use the discrete Fourier transform, and here we can see that these are the samples, digital. This is a digital signal. Let's say this is a voltage signal, and these are all the instantaneous discrete sampled values of the instantaneous voltage signal. Here we calculate the angle, the sampling angle. So this is the non-recursive method. Actually, we are doing it only for one window, but if we keep on doing it for all the windows without using information from the previous window, then it becomes a non-recursive phasor update. We will see it in the next slide also. Then here we will calculate the angle cos of that sampling angle, theta, and here sine theta. Then xn cos theta and minus xn sine theta. And from these two values we can derive the phasor. So this will be the magnitude. This is the peak magnitude. And if you want the phasor RMS value, we generally represent phasor by RMS value and divide it by √2. If you directly want it √2, then this should be √2. Take it as √2. then you will get this you will get here divided by root 2. Angle will not change. The 2 pi by, so n goes from 0 to 7, 0, 1, pi by 4, 2, 3, 4. 4 it becomes 5, 5, 6, and 7. For each of these, we calculate cos and sine values and multiply it by xn, and we sum each of these. Then we get xr and xi, real and imaginary part. And then if you want the magnitude, then directly this RMS value, let's say this is V, then it will be xr square plus x real and imaginary square. This will give us the voltage magnitude, phasor magnitude, and this will give us the angle, tan inverse xi by tan inverse xi by xr. We can calculate both the magnitude as well as the phase. So this phasor will be 220.47 by root 2 angle minus 70.03. This is the phasor. I hope it's clear. Okay, let us move to the next part then. Yeah, we're talking about the recursive and non-recursive part. Here, this is non-recursive. These are the two ways of updating phasor. Let me just have a sip of water. Yeah. So these are the two ways of updating phasor. One is non-recursive and another one is a recursive way. In non-recursive, what happens is that the phasor magnitude remains same, but the sampling rate, not sampling rate, sampling angle changes from 0 to n minus 1 to 2 pi n by n, and n varies from 0 to n minus 1 as we have seen here. Here. Huh? Here we can see n is 8, so n goes from 0 to 7, 8 minus 1, and this is done for each window, and each window has samples, number of samples is 8. We can have more samples also, but here we are taking 8 samples, and for each window we'll do the same thing. And let's say we have here we have 1 to 10 samples. Okay, that means just add one page itself. It will be more clear, better, because this page is already filled. Insert a blank page. Okay. Yeah. I was talking, let's say we have 10 samples. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And because n is equals to 8, that is number of samples per window. This is window 1. Yeah, I will show window second by a different color. Take blue color here. This will be window 2. So in window 1 to 8, then window 2, 8 window moves ahead by one measurement. Here, that's why we see the angle also changes by one measurement. Similarly, third window will be like this. This will be the third window. Okay. This will give us one, all these three will give us three values. So here will be voltage magnitude will remain same. Angle will be angle 3. Here this will give you V angle theta 2. Angle theta 1. Here this will happen. For each window, we are again doing the DFT. So this is non-recursive phasor update. Every time we have to do the DFT. But there is another way where recursive phasor update, where we say that if I have already calculated the phasor for this window 1, why don't I use this information, this phasor estimate for first window for calculating the phasor estimate of second window? That is done here. So in that case, what is done? The angle difference between this first and the ninth. See? So this difference is used. So the incoming measurement and the outgoing measurement phase angle difference is used. Because here this will be what? 2 pi 8 by 8 minus 2 pi 0 by 8. The angle difference is 2 pi. And this is used. So here we are calculating new phasor. For a new window using phasor estimate of previous window. So anyhow, we have to do this continuous evaluation. Either we use a recursive or non-recursive. We need to do this continuous phasor estimation because the signal, the voltage and current signal, they are continuously coming. The PMU, the CT and PT are continuously measuring, and PMU is getting the input from these measurement on a continuous basis. Continuously it is getting. And then window by window it is calculating. And for each window it is calculating. And when, how the fault detection happens, that suppose we are calculating, and for each, let's say this window, difference between the phasor estimate of previous, these two window, if it increases to a large value, and if it uh, goes beyond a threshold, then we will say that current, there is a fault because current has increased too much. Normal operation, what will happen? The current will remain same. The magnitude will remain same in normal operation. But in case of fault, it will change. In case of fault, there will be a sudden increase in current. And that can be used to detect fault. We need continuous evaluation for continuous monitoring of the state of the system. Yes, I think this is clear now. Cursive and non-recursive. So here the phasor rotates in the counterclockwise direction with a constant magnitude and a sampling angle theta. We have already seen this. But here there is an angular retardation of theta. Because we take the difference of angle and then we multiply it by is d2 pi n by n. This makes the phasor stationary. The same thing we discussed, that phasor calculation are done afresh. It's a continuous word. Afresh. So again and again we have to do it for each window. This method is numerically unstable. This is stable, but this is numerically unstable sometimes. This is unstable. This is computationally intensive because for each window we are estimating the phasor. But here, and because here we are using the phasor estimate of the previous value to estimate the phasor of the new window, if there is an error in the phasor estimation of the previous window, it will propagate in the subsequent windows, all the subsequent windows. And therefore, this creates a problem. There is error propagation continues. And it is computationally efficient. That is why it is popularly known and it is used. So just calculate DFT once and then use it. That's why the problem is, if the first calculation which we are doing, if it is prone to error, then the entire calculation becomes error. It becomes prone to error. Now we will see the another method of Phasor estimation. This will work only for the periodic signals where we have voltage and current signals don't have any DC component. But if we have a DC component and we want to capture that also, then we need to use another method, which is a linear least square method, least square estimation. I will use this slide again, blank slide again. Let's suppose we have a signal here, IT as I1 sine of omega naught t plus phi plus a DC component, let's say, which is k naught e raised power minus t by tau. Tau is the time period of the signal. So we know that t can be written as NTS because number of sample is equals to t divided by sampling time. Okay, sorry, I can write. Yeah, the t we can replace by NTS. Then this will become sine of omega and omega naught ts plus phi. Omega naught and ts are known. This is frequency fundamental component 2 pi f naught, and the sampling time also we know based upon the sampling frequency which we have decided, and ts by tau. Okay, so here provided, let us assume here we know the time constant tau, then e raised power minus n e raised power minus ts by tau we know, and we call it as r. Now expand this. This is I1, use identity. This becomes sine A cos B plus cos A sine B plus the DC component. E raised power, let's say, R raised power n. Okay. Now we can write this. Unknown here is I1 is unknown and phi is unknown. Sine n omega, because omega naught t we know, this is known. This is the unknown, we let us call it as A. And this is I1 sine phi cos of n omega naught ts. This is another unknown here, plus k naught into Rn. And this is another unknown, let us call it as C. Other things are unknown. This is known. These are known. This is, let's call A1. This is A12 and this is A13. And now we let us call these as ABC. ABC is, I was using the same notation was in lecture, but let us call that this unknown, generally we represent them by X vector. Let us call them X1, X2, X3, and this is the known vector. So this becomes A12, A1, A11, A12, A13. This is I and T. So let us say we have n samples. Then n varies from 0 to n minus 1. Now we can make it form a matrix here, which will, this will be sine and 0, sine of 0, cos of 0, 1, which is 1, and this will become as r raised power 0, which is again 1. Now here second element will be, so this will be here I of 0, I of ts, so on up to I of n minus 1 ts. Okay, so this become omega naught ts cos of omega naught ts, and this become e raised to power minus ts by tau, so on, so on, so on, up to sine of n minus 1 omega naught ts cos of n minus 1 omega naught ts and e raised to power minus n minus 1 ts by tau. Okay, and this we call as the A matrix, and here we have this, we call it as B matrix, and here we have x1, x2 and x3, which are the unknowns. Now we have simple equation Ax is equals to B, system of linear equation. Then x, where A plus, this A is not plus, actually this is a dagger. So A dagger B, this A dagger is called as the pseudo inverse, and which is equals to A transpose A inverse A transpose B. And there are ways to avoid this inversion operation. We can use different decomposition techniques, factorizations to do it. Simple one thing is use QR or SVD also can be done. All these things can be done. Sorry. Yeah, so we can do all these things, and then now let me just write it here. Now suppose now you have x1, you have calculated x1 is I1 cos phi, and x2 comes out to be I1 sin phi. Now x2 divided by x1 is 10 phi. So phi is equals to tan inverse of x2 by x1, and I1 will be equals to root of x1 square plus x2 square. That's how we can calculate I1 and phi, and this k0 is simply x3. This is the case where we already know the time period tau, but generally we don't know. We don't know the time tau, this tau also. So now let me do it for that tau. When tau is unknown, in that case, this will change. One more, because one more unknown is going to come, so one more column we need to append here. Let's say we don't know this time constant also. Then we can write the Maclaurin series of this e raised power t by tau. We can write it like this. Then it becomes k0 minus n is known, k0 by tau, this is unknown, and nts is known. Okay, now this becomes your x3, and k0 by tau becomes your x4. And so what will happen here? Here you will get 1, 1, 1, 1, and the next column will be minus. So this will be 0 because for n is equals to 0, this will be ts minus ts. and this will be minus n minus 1 ts. Now here we have 4 unknowns. One is x1, x2, x3 and x4. All these are still valid. The only thing is changing here. X3 is x k naught. This is also same. But now x4 is equals to k naught by tau, which is equals to x3 by tau. So tau is equals to x3 by x4. K naught is x3 and tau is equals to x3 by x4. Okay, this is done for both the cases with when we know the time constant, when we don't know time constant. In both the cases we can do it. We have done it. Now let us move to the next part. This is the same thing I have explained here. Now synchrophasor standard C37. You can remember this. What are the standard for synchrophasor? The standard for synchrophasor is this one. We have C37.IEEE. So this is the IEEE standard. IEEE C37.118.1. Synchrophasor standard. Please remember this. And here these are the standards that accuracy which has to be maintained for the PMU. It's the maximum permissible total vector error is 1% TVE, and this is the difference between the estimate minus actual square sum divided by the actual square sum of actual square. So this should be less than 1%, less than equals to 1%. And synchronizing error, because we have between two PMU measurements. Because we have for 50 Hertz, the maximum synchronizing error can be 1 microseconds. Whether it is 50 or 60 Hertz, but this 1 microsecond translates to this 360 into 50 into 10 to minus 6. It translates to 0.018 degrees. This can be this is the maximum permissible error. Similarly, we can calculate it for 60 Hertz also. And the standard also defines two types of PMUs. One is class P, which is the protection class PMUs. Here in protection, our main emphasis on speed of measurement. Here measurement speed is very important instead of the accuracy, over accuracy. Here we want less latency in the measurement. Measurement latency here is maximum measurement latency is 2 by fs. So 2 ts. Okay. Then another one is the class M, which are the measurement PMU. Measurement PMUs. Here accuracy is important. Accuracy is important over speed of measurement. And here the maximum latency in measurement is, I think, 5 by fs. I can see here. Let me just erase. Here maximum latency is 2 by fs and here it should be 5 here. There's a mistake here. This should be 5. So this is 5. This is 2 by fs. This is 5 by fs. Then factors for latency. What are the reason for these delays? One is the measurement latency. So in measurement, we have these different blocks. We have already seen so many blocks are there. We have ADC, we have filter, and PLL also. So many things are there. Then another source of latency is the communication coding, because we use this encoding and decoding so that there is no attack to avoid that attack, cyber attack. Then we have transmission distance also. If distance is more, it will take more time. These three are the three sources of latency. Now we'll move to the optimal PMU. Now that we have known that we have PMUs, and using DFT they are able to estimate phasors in which are transmitted to the control center. Okay, very good. We are able to get information regarding voltage and current phasors, but where do I keep PMUs? If I decide to have PMUs at each and every bus, then I will have to, what will I have to do? If I decide to have PMU at each bus, then one thing is I have to discard replace all the SCADA, replace all the SCADA RTUs with PMUs, all the and then replace the remove this existing state estimator and now replace it with the new. All these things we need to do if I decide to do, but this comes at a huge cost. Overhaul, entire overhaul of the existing system, full change overall, which is a costly affair, and that's why government will never do that. That's why we have PMU installation. In an incremental fashion. And now if we want to do it in an incremental fashion, then we need to know which buses to choose first. Optimal buses, optimal numbers plus locations. Here we are talking about this, but in India we did that We install them. I think now we have all at 400. All the substation 400 and above kV. So this is a very important thing to do to calculate the number, optimal number as well as location. So that is our next topic. And to and this optimal number and location is derived is driven by a very important concept of observability, which says that to observe or to measure the entire state of the system, minimum number of measurements are required. And those states can be uniquely determined from if the states and for us states are these voltage magnitude and angle at each bus. These are the states. And these states, if they are uniquely determined from the given measurement, we call the system is observable. And for this, we can detect the unobservable line and identify the observable islands. These are the two techniques which are used. One is the numerical, sorry, techniques for observability. One is numerical, another one is topological. This uses algebra, matrix algebra concepts or different factorizations. And this is based upon graph theory, concepts from graph theory. Now there are different ways to do this optimal placement also, and these are these techniques. One is exhaustive search. This provides a global solution, but it is only suitable for small number of candidate PMU locations. For large number, for a large system, it becomes very difficult, computational, challenging. Then next is the integer programming. This can be used for large system. Intelligent techniques for optimization. This is also not suitable for large system. So our solace, we get solace from this. Our friend is integer programming. These are the rules for observability. Let's say I have this bus, this one bus, bus one, and it is connected to these buses. If I have a PMU over here at bus one, let me derive with a different color. So I have a PMU here at bus one. And this PMU can measure voltage phasor at bus 1, bus 2, bus 3, bus 4, and bus 5. because because it measures the voltage at bus 1 and all these currents, branch currents. Once branch currents are known, we can easily calculate the voltages also. But if there is bus, let's say we have this bus 2 bus. Let's say we have another bus here, bus, sorry, bus 6 and bus 7. And this 7 bus is connected to some other bus, let's say bus 8, and we have a PMU here. This PMU will be able to calculate the voltage phasor of 8 bus 8, a current in all these lines. So this voltage phasor is known by PMU 2, and now we know this by PMU 1. And because we know the angle here, we know angle here also. We can calculate the angle here using KCL. Because we know this current. This current is known, and this current is also known. This voltage can be known. Yeah, the same thing is written here also. These are the rules for observability. A PMU at a bus can measure phase angle of voltage at that bus and phase angles of voltage at the bus at the other end of all the incident lines using current measurement. Zero injection buses, KCL, can be used to find angle of one bus using angle for all other buses. But this can lead to propagation of measurement and parameter errors. Parameter are these the line parameters. If there is an error in the estimation of line parameters, then that will propagate to the other bus also, bus measurement. Now here we move to the formulation for optimal PMU placement. This is a mixed integer quadratic program. Here because we see objective function is quadratic. And this x is an integer. It's a vector of integer. A is a connectivity matrix. Which we see here. A, let us say we have this 3 bus system. Bus 1, 2, and 3. And connectivity matrix says, how are you going to formulate it? It says that if I is equals to j or AI, the diagonal elements are all 1. Diagonal are all 1. Then if line is connected to that between two buses, then that entry is 1. So 1, 2 is 1, 1, 3 is also 1. 2, 1 is 1, 2, 2 is 1, 2, 3 is 1. 3, 1 is 1, 3, 2. So this is an identity, sorry, it's a one matrix. All entries are one here. But if we have a fourth bus also here, then the connectivity matrix will change. Here, there is no connection between 1 and 4, 2 and 4, and 1 and 4, 2 and 4, 3 and 4 there is a connection, and 4 for diagonal element will be 1. This will become 0, 0, 0. So this will become 1. So this will be the connectivity matrix. It is same thing is written here that Aij is 1 if I is equals to j, that is all the diagonals are 1, and if I and j are connected, otherwise 0. And xi is 1 if PMU is placed at the bus I, otherwise it is 0. The product A into x says that it tells the number of times a bus is observed by the PMU placement set defined by x. And we want each bus to be observed by the set defined by x at least once. If I want to keep a redundancy, then we can make it 2. Okay, let us now say this part is done, connectivity matrix. Now let us move to the objective part. What does the objective says? So here we have two components. One is this cost, where Q is the cost of installation. Q here is a diagonal matrix because we say the cost of installation at one bus is not dependent on the cost of installation of second bus. They are independent. Then we have R matrices. R gives significance to each bus. If some buses are more important, we can give more weightage to that bus. Same thing we also use in the state estimation when we want to give more weightage, higher weightage to the measurements with less variance. Therefore, in that case, the RII entry becomes 1 by sigma I square. Sigma square is the variance. So if variance is less, that measurement is given more weightage. Same thing, if here the significance of a bus is more, that corresponding R diagonal element is higher. And this is some weight. Now here n is the number of number of times you want the bus to be observed. Okay, minimum number. Yeah, so where were we? Yeah, if the buses are equally significant, that means this R will become an identity matrix. And if cost of installation to each bus is same, then Okay. Now same thing. And here we are expanding that. We are making it more general. Now if we multiply this, we expand this, then we will get this lambda n transpose Rn minus 2 lambda A 2 lambda n transpose Rax, because here also we have lambda n transpose Rax, and from here also we'll get lambda 2 n transpose Rax plus lambda x transpose A transpose Rax and plus this x transpose Qx. Now we club the x transpose terms, this and this. Then what will you get? Half x transpose 2 lambda A transpose Ra, this lambda A transpose Ra plus 2q. Combine these two terms. Now this term Ax minus 2 lambda n transpose Rax plus lambda n transpose Rn. Because R is known, N is known, N is known. All these are, this is a constant. This is F transpose. Now we have brought it in this form into this form. This form, half X transpose Gx plus F transpose X subject to Ax greater than equals to B, where G is, where this is G and this is F transpose. And B here is equals to I and correspond. Actually this not, it should be 1. Okay. Now this is without any contingency. But we want in either of these two. If one line goes out or one PME goes out, then also we should be able to assess the state of the system. For that, we will need extra PMUs. For that, we need to add more constraints. These are the constraint for loss of transmission line. If there is a transmission line between bus I and J, then in connectivity matrix, we have Ij is equals to Aji is equals to 1, right? But if you want to remove this line, then we need to update Iai is Ij Iji is equals to 0. Update this, and then corresponding two rows Aij sorry, AI and AJ. Multiply them with X, and they should be greater than equals to 1. This constant we need to add. So similarly here what we'll get on a matrix. We have set of these two rows for each contingency, and this will get 1. And here it will be 2 NB cross 1. The size of this vector 2. NB is the number of outages, branch outages. Okay. So this will be the additional constraint. A1x greater than equals to B1. And the second is when there is an outage of a single PMU. In this case, we simply change AX is greater than equals to B2. Where B2 is equals to 2 into 1 and cross 1. Replace B by B2. So we are increasing a redundancy number of redundant PMUs by 1 at each bus. And that's how we'll be able to ensure that, because if one PMU goes, since we have a redundancy level, that will be covered. So that PMU will be observed by 2 buses. Now, if you want to include the conventional measurements in this PMU, optimal PMU placement, inclusion of the conventional measurement in the optimal PMU calculation. Here what we can do, here the system is such that there are more than one island which are observable by conventional measurements. So we have different islands and each of them are observable by SCADA measurements. There are enough number of measurements. Krishna. Sorry. Now problem is to find the optimal number on locations of PMU to make the system observable as a single island. Yeah. We have to find out the optimal number and location of PMU to make the system observable as a single island for both normal operating condition as well as outage of single line or single PMU. We have already discussed how to handle outage of a single PMU and outage of a single line. Now here only thing which is additional is there are number of observable islands and we want to make them a single observable island. So PMU have to be such that. So here we want to identify the unobservable branches. And to ensure the observability under single line outage, it is sufficient to make sure that the system is observable for outage of any of the unobservable branches. So here under normal operation we have sk into x is greater than equals to 1. Where ski is 1 if bus I belong to that kth observable island. Or it is connected or the bus I is connected to a bus in the observable island. Otherwise, it is 0. So this is under normal operation condition. Under line outage, this Sk is replaced by Sk dash. Corresponding to that line, it will become. And for single PMU outage, we already know we have to increase redundancy by 1. So just replace 1 by 2. And these are the different measurement uncertainties in PMU. The sources of these measurement uncertainties first comes from the instrument transformer because of the calibration problem. Then comes from the cable which are connecting the instrument transformer and the digital equipment. Then last is the AD converters and the associated computational algorithm. So these are the typical value of errors permitted by the manufacturers. The voltage magnitude error is 0.02% of the reading, current 0.03% of the reading, and phase angle is 0.01 degrees. Now, how to treat these measurements? So now we are moving towards the state estimation. That's state estimation. Yes, state estimation only. So here, measurements other than phase angle, they are considered as independent. Therefore, the weight matrix for them becomes a diagonal matrix, where the diagonal entry is equals to ui square and ui is equals to delta u by root 3. Where ui is the center uncertainty in the measurement. For phase angle, the RII diagonal matrix diagonal element is equals to ui square plus u0 square, because here the phase angle of, if any one phase angle 0, there are chances other are also going to be affected by that, because here the phase angle, this should be Rij. Rij is equals to self square plus mutual square. Not mutual, it is with respect to the phase angle of all the buses with respect to the slack bus phase angle. Rij is equal to u I square plus u naught square, and Rii is equals to u naught square. So this is for the phase angle. Now we'll move to the hybrid state estimator. In hybrid state estimator, there are two methods. One is post-processing and another one is the pre-processing. Post-processing and pre-processing. So these are the two methods which are used in two different situations. The situation which we are in currently, presently, where we are incrementing or including PMUs in an incremental fashion. The post-processing is a more practical approach where we use the SCADA, output of SCADA. output of SCADA it gives it is an input to the hybrid state estimator which gives the state estimation. Here we have PMU data. PMU data also. Same thing is written here also. Output of PMU earlier old plus new is equals to new. So this is practical now, where we are doing installation in incremental fashion. Here the process is we mix the PMU measurement with output of the existing state estimator and then do the estimation. Now this hybrid state estimator can be linear as well as non-linear. For linear update, we can see here the new XRE and XIM are the X factor here is the voltage. So these are the voltage real and voltage imaginary. X is voltage real, new, imaginary part. And this is equals to A transpose A. This is A dagger B, where A dagger is A transpose A inverse, A transpose B. Only thing which is additional here is the weight matrix. The weight matrix here is this W. So after using this gain matrix, it is A transpose W A inverse into A transpose W into this B, which is composed of two parts. One is the measurements of PMU, and this is the output of existing state estimator. It's output of existing state estimator. Okay, so here also we are getting the voltage and imaginary part. So this becomes a linear state hybrid state estimator. Then we have nonlinear also. The nonlinear update equation is this one. Here xk update xk is equals to xk plus 1. Sorry, this should be xk minus 1. Plus h transpose wh inverse into h transpose w into z minus h xk. Pre-processing is a futuristic hybrid state estimator. Here both the conventional and PMU measurements are processed together. In the previous, this post processing is a sequential approach. First, we are solving the conventional state estimator, and its output is going to its output along with the PMU measurement goes to the hybrid state, to the linear state estimator. We have a conventional state estimator. Here we have inputs. And this will give you output, and this goes as input plus PMU measurements also, linear state estimator. Then we get the new estimate. This is the post-processing. But pre-processing here, pre-processing, what is happening? Direct, it is a hybrid state estimator. It takes input from PMU also. It takes input from SCADA also, and directly gives the estimates. Here we need to, problem is of aligning the, because one is timestamp. This is not timestamp. Another problem, varied. Okay, varied refresh rates. Very different refresh rates. How do we combine them? This is coming at very fast rate, this is coming at a very slow rate, and one is time stamped, one is not time stamped, which it's very difficult. So these are the different challenges which need to be overcome for this futuristic state estimator. Okay, directly here we will get angle and voltage if it is polar coordinate. Otherwise, you can get V real plus V imaginary also. Same thing. The voltage measurements can be directly incorporated here. But current measurements, there are three ways to do that. Either take voltage, current magnitude and phase, or real and imaginary part, or generate the pseudo voltage measurements. So here we take conventional PMA measurements and process them together. Then it will require modification in the existing. We need to change the existing state estimator completely. Voltage measurements can be included easily, but current measurements, there are three ways. One is either use, this is polar form, this is your Cartesian, the polar coordinate system. And this one, third one is to have pseudo voltage measurement with the help of current phasor measurement and known line parameters. If we have this line, I know I have a PMU here. I don't have a PMU here. I know the voltage here. And I know the voltage here. So I can calculate the current here if I know the line parameters. And another challenge here is the presence of current magnitude that tends measurements. Current measurements in the matrix, it tends to make the matrix ill conditioned. The gain matrix ill conditioned. This is another very big problem. So after this, we discuss the dynamic state estimator. And the rotor angle estimation. Which is important from the stability perspective. important from the power system stability perspective, because we know that we have this power angle curve. Initially, we're operating here, and if there is a fault suddenly, then the electrical output becomes zero. And it is cleared after some time. If it then it will reach here. We have this an equal area criterion. And we used to calculate the angle. Okay, power system stability parameters are important. Dynamic state estimator, as soon as we get a measurement, we use that. By using the previous state estimation, add this new measurement and provide me the new state of the system. And this can also be used to predict future states, future state of the system. And then based upon this prediction, give control, take necessary control action. We can do some preventive measurements or preventive control also. Corrective as well as. Mostly it will be preventive because we are looking into future. The dynamic state estimation can help in that. I think next class will be also very important. Next class we will discuss the control part. This is also part of control. This is operation. This is estimation of the state. Then once estimated, how do we control it? There we have this generation control, automatic generation control, automatic voltage regulator, AVR, and automatic generation control, AGC. These things we need to understand now. We will see different models. We will see the turbine model, generation model, load model, tie line model. All these we will try to connect them and find out the area control error and all those things. So we will see how to restore the frequency, how this automatic generation control works within this group characteristics, group control to restore the frequency. To a new stable value, new equilibrium. It can be same as the old also. But yes, all these things we will see in the next class. Now let us move to the questions. Questions are also easy today. So this is the first question. A 4-pole 150 MVA. Actually, this will come in the next class also. 15 kV 60 Hertz alternator has an inertia constant of 12 megajoule per MVA. And if the input of the generator is suddenly increased to 80 megawatt for a load of 60 megawatt, the magnitude of acceleration of the rotor will be in degrees we want to know. We can use this equation. We know that P mechanical minus P electrical is equals to md square delta by dt square, and we want to find out this. This is the acceleration of the rotor angle of rotor. So first we need to find out m. We have S 150 megawatt and H is given as 12 megajoule per MVA. 12 megajoule per MVA. We need to find out M. Frequency is 60 hertz. And so M is, this is H only. S into H divided by 180 into F. 150 into 12 divided by 180 into 60. This becomes 5. This is 3. 6. 1 by 6. 1 by 6 megajoule per electrical degree. Megajoule second. Electrical degree per second. From swing equation, this is a swing equation we already know. This is known. Sudden increase in 80 minus 60 divided by 1 by 6. It becomes 120 electrical degree. PA here is acceleration power. Okay, next one is find the inverse Fourier transform of 6 plus 4 j omega. So what we can do? Replace j omega by s. So 6 plus s. This becomes s square plus 6s plus 8. This becomes your axis. Now do partial fraction. A by s plus 4. B by s plus 2. So this becomes s plus 6 is equals to a times of s plus 2 plus b times of s plus 4. Substitute now s is equals to minus 2. This becomes 4 is equals to b. B is equals to 2. S is equals to minus 4 plus 2. A minus 4. Have I done something wrong? S is equals to minus 2. This is gone. Minus 2 plus 4, 2. Minus 2, okay. Oh, this is 4s. So this is minus 2. 4 into minus 2 minus 8. This will be minus 2. So B is minus 1. Yeah, minus 4. 16. So this become minus 10. A minus 4 plus 2 minus 2. This implies A is equals to 5. So xs is equals to 5 divided by s plus 4 minus 2 divided by s plus 2. You can take inverse Laplace. You will get 5 e raised to power minus 4t minus 2 e raised to power minus 2p into u of t. Now at t is equals to 0, this becomes 0. 5 e raised to power 0 is 1 minus This is minus 1. Minus 1. U0. This becomes 4U0. So answer is this is C and D. Discard. This is C and this is D. Okay, so this is a solution. Now, angle between successive PMU measurement and non-recursive n is equals to 50. So we already know sampling angle is 2 pi n by n. And if n is 1, so it becomes 2 pi by n into pi by 180 by pi if we want it in degrees. The pi is gone. It is 2 into 180 divided by 50. So this becomes 7.2 degrees. Similarly, you can calculate it for 60 degrees, 60 hertz also. Permissible synchronizing error for PMU for 60 hertz system. Yeah, so we know it is 1 microsecond. So it becomes 10 to the power minus 60 hertz into 10 to the power minus 6 into 360 degrees. How much is this? 0.0216. Class P PMU does not have anti-aliasing filter. Protection class measurement here, speed is more important than accuracy. Speed is important, so they will avoid filters because filter will delay. They will add a delay. So this is true. Very. So here what has happened? PMU protection class. Protection adds, filter adds a delay. Increases latency. We want speed over accuracy. The recursive Phasor update encounters problem of error propagation. Correct. This is true. We have seen techniques for observability analysis. There were two. One is numerical and one is topological. This is based upon graph theory, and this is based upon matrix algebra. Oh, so these are the questions. End of all the questions. I hope you are able to understand. If you have any doubt, you can ask in the next class. Thank you. Thanks all of you for joining the session. I will upload these PPTs and I think you will find answer here. Yes. I will upload these PPTs. You can go through this and we will meet next class. Thank you.